Welcome everyone, and thank you for being here today. I'm excited to introduce our presentation on Module 2, Chemistry of Nutrients. Today, we'll be focusing on Study Session 3, which covers water, acids, bases, and buffers. This is part of our BCHM 241 course on the biochemistry of macromolecules. Over the next few minutes, we'll explore how these fundamental chemical concepts relate to nutrients and biological systems. So let's get started. Today, we're going to explore the properties of water and understand why it's so vital for life. Water is not just a simple molecule. Its unique properties support all biological processes. We'll look into its biological importance, such as how it acts as a solvent and helps regulate temperature. Next, we'll delve into the concepts of acids, bases, and buffers. These are crucial for maintaining the stability of biological systems. Understanding how acids and bases interact and how buffers work will give us insight into the delicate balance necessary for life. Throughout this slide, I want you to see how these properties and concepts connect to the broader theme of biological stability and function. Water's properties are fundamental to maintaining life's harmony at the molecular level. Water is a molecule formed from two elements, oxygen and hydrogen. The oxygen atom creates a covalent bond with two hydrogen atoms, resulting in the familiar H2O structure. What's really interesting is that the oxygen in water is highly electronegative, meaning it pulls electron density towards itself. In contrast, hydrogen is electropositive, so it tends to have a slight positive charge. This difference makes water a dipolar molecule, with a positive and a negative side, which also means it has a slight tendency to dissociate into ions. Because of these polar characteristics, water molecules can interact with each other through intermolecular forces. Each water molecule can form hydrogen bonds with up to 4 neighboring water molecules, creating a network of interactions that are crucial for water's unique properties. Additionally, depending on the polarity of other molecules present, water can also form intramolecular interactions, which influence how substances dissolve or react in water. Understanding these properties helps us see why water is such a vital solvent and plays a central role in biological and chemical processes. It's these interactions and behaviors that underpin much of what we observe in the natural world. Today, I want to talk about the lattice structure in ice, which is a fascinating aspect of its molecular arrangement. Essentially, the way water molecules organize themselves in ice forms a specific, repeating pattern known as a lattice. This structure is critical because it explains many of ice's unique properties, like its solid form being less dense than liquid water. In the lattice, each oxygen atom is bonded to 4 neighboring hydrogen atoms, creating a tetrahedral shape. This arrangement results in an open, spacious structure that's responsible for ice's lower density. It's quite interesting because it means that ice floats on water, which has significant implications for our environment and ecosystems. Connecting this to the overall theme of molecular structure and phase changes, understanding the lattice in ice helps us see how molecular arrangements influence physical properties. It's a perfect example of how microscopic structures directly impact what we observe at the macro level. Water is the predominant chemical component of all living organisms, accounting for about 70 to 90% of their total mass. This high water content is crucial because water creates the aqueous environment necessary for biochemical reactions to occur efficiently. Without water, many of these vital reactions simply wouldn't take place. Additionally, water provides a supportive environment for macromolecules like proteins and nucleic acids to achieve and maintain their stable structures in solution. This stability is essential for their proper function within cells. So, in essence, water isn't just a simple substance. It plays a central role in maintaining life by enabling biochemical processes and supporting molecular stability. It's truly the backbone of biological activity, connecting to the broader theme of how essential molecules sustain life. One of the key properties of water is its ability to ionize, meaning it can produce ions such as H+ and OH. These ions are constantly forming and recombining, so their concentrations exist in a state of equilibrium. This equilibrium is important because it gives water the ability to conduct electricity. Now, the ionization of water can be described by the equilibrium constant, K, which is equal to the concentration of H plus times the concentration of OH divided by the concentration of water. Since pure water at 25 degrees Celsius has a concentration of about 55.5 molar, we can substitute that into the equation along with the electrical conductivity value, which is approximately 1.8 times 10 to the minus 16 molar. When we do that calculation, we find that the product of the concentrations of H plus and OH equals roughly 1 times 10 to the minus 14. At neutral pH, the concentrations of H plus and OH are equal, so we can set H plus equal to O, and their product becomes H plus squared. Taking the square root of 1 times 10 to the minus 14 gives us H plus, approximately 1 times 10 to the minus 7 molar. From there, calculating pH is straightforward. It's just the negative log of the hydrogen ion concentration. So pH equals 7, which is considered neutral. This ionization process is fundamental because it explains how water can act as a medium for various chemical reactions and electrical conductivity, tying into the broader theme of water's chemical behavior and its importance in biological and chemical systems. Now, let's take a closer look at calculations. This slide is all about understanding how we quantify and analyze the data we've been discussing. Calculations are the backbone of turning raw information into meaningful insights. They help us measure performance, identify trends, and make informed decisions. I'll walk you through some key formulas and methods we use, emphasizing how each one connects to our overall goal of improving outcomes. Remember, precise calculations lead to better strategies, so paying attention to these details is crucial. As we go through, keep in mind how these figures support the bigger picture of our project and objectives. An acid is a compound that dissociates in aqueous solution to produce a proton, which is a hydrogen ion, and a conjugate base. This process can be summarized by the equation Ha equals H plus A minus. Now, acids can behave differently depending on how much they dissociate. Some acids, called strong acids, dissociate completely, while weak acids only dissociate partially. In the case of a weak acid, an equilibrium is established between the undissociated acid, the proton, and its conjugate base. For example, the acetic acid dissociation constant, Ka, is given by the concentration of the conjugate base times the concentration of the proton, divided by the concentration of undissociated acetic acid. The acid dissociation constant, Ka, is related to the pK value through the formula pK equals negative log of Ka. This relationship helps us understand acid strength. As the acid gets weaker, the pK increases. Now, when we start with an acidic solution, the pH is low. If we add hydroxide ions, OH-, to the solution, the pH gradually rises. It continues to increase until it reaches the pK value. At this point, the pH stops changing sharply, and importantly, the concentrations of the weak acid and its conjugate base become equal. This is what we call the buffering zone. Here, the solution can resist pH changes effectively because the weak acid and its conjugate base work together to maintain stability. Understanding this balance is key to grasping how acids behave in different solutions and how buffers protect biological systems and chemical processes. This slide doesn't contain enough information. That's why we're moving to the next slide. This equation is particularly useful when we're preparing buffer solutions. It helps us with 3 key calculations. First, the pH of the solution. Second, the pK of the weak acid involved. And third, the molar ratio of the weak acid to its conjugate base. The equation itself is derived from the dissociation constant of a weak acid, which is expressed as Ka equals the concentration of hydrogen ions times the conjugate base over the weak acid itself. To manipulate this, we solve for the hydrogen ion concentration, H+, which gives us Ka times the concentration of the weak acid divided by the conjugate base. Taking the negative logarithm of both sides allows us to express pH directly, because pH is just the negative log of H+. When we do that, we get this expression. Negative log of H+ equals negative log of Ka minus the log of Ha over A's. Now, recognizing that pH is defined as negative log of H+ and pK is negative log of Ka, we can substitute these into our equation. This simplifies to pH equals pK minus the log of the ratio of Ha to A. If we invert that ratio inside the log, we arrive at the Henderson-Hasselbalch equation. pH equals pK minus the log of A over Ha. This equation is fundamental because it links the pH of the buffer solution to the ratio of conjugate base to weak acid, which is crucial in buffer preparation and understanding how buffers resist pH changes. Let's take a closer look at the calculations involved here. First, it's important to understand that these calculations are the backbone of our analysis, helping us quantify the key variables we discussed earlier. When we talk about calculations, we're really talking about breaking down complex data into manageable, understandable numbers. One of the most important concepts to highlight is accuracy. Small errors in calculations can lead to big differences in outcomes, so precision is crucial. As we walk through the formulas, keep in mind how each component connects to the bigger picture, how they support our overall goal of making informed, data-driven decisions. In essence, these calculations enable us to turn raw data into actionable insights, which is at the heart of our entire presentation. They serve as the foundation for everything else we're discussing, so mastering these steps is key to understanding the full story. All right, let's look at this scenario. We have a 10 ml sample of gastric juice taken a few hours after a meal. This sample was titrated with 0.1 m NaOH until it reached neutrality, and it took 7.2 ml of the NaOH to do so. Now, since the patient hadn't eaten or drunk anything, we can assume there were no other buffers present in the stomach contents. The key here is understanding what this titration tells us about the original pH of the gastric juice. Because we added a known concentration of NaOH until neutralization, we can determine the amount of hydrogen ions initially present. From there, calculating the pH becomes straightforward. This example underscores how titrations can help us analyze the acidity of biological fluids, which is essential in understanding gastric function and health. It also ties into the broader theme of measuring and interpreting pH in physiological contexts. So, by knowing the volume and concentration of NaOH used, we can work backwards to find the initial pH of the gastric juice, giving us insight into the stomach's acidity several hours after a meal.